Hello, my name is Steve Miller. I'm a math professor at Williams College, and this is part of Probability Lectures, Die Another Game. So the title is inspired by a James Bond movie, not the one pictured here. This is Octopussy, which has a great backgammon scene involving double sixes. The YouTube link is here. It's a very entertaining probability calculation. What we're going to do today is we're going to talk about some games, and they're going to use some of the results we proved last time in the May the 4th lecture when we looked at the Darth Vader problem. So all of the lectures are available at the link on the bottom. And as always, it's a pleasure to thank the Journal of Number Theory and the teachers as well as programs. Unfortunately, there was a video recording malfunction, and so I'm going to record this without my teaching assistants today. So it'll be a little faster potentially. All right, so what was the Darth Vader problem? So the probability of failing a task is P. How many tasks until you die? This was because Vader kills you at the first failure. And we showed that the answer was 1 over P. So an equivalent way of looking at this, a more positive, happy way, is that the probability of success is P, and the number of tasks or tries you need before your first success is just 1 over P. And we can use that to study a new game. And we'll call this the sixes game. You roll a fair die until you get a 6. You keep rolling and rolling and rolling, and as soon as you get a 6, you stop. And the question is, how many rolls do you expect before this happens? So this is a good place to stop the video and think about the question. All right, welcome back. So the answer for this is just 6. And the reason is it's the Darth Vader game. And the probability of success here is just P equals 1/6. So we have 1 over P. That's the reciprocal of 6, which is just 6. So we're going to now make the game a little bit more interesting. We're going to call this the double sixes game. So you have 2 fair die. On each turn, you can roll 1 of the die or both. And the goal is to have both show a 6. So obviously, once 1 of the die lands on a 6, stop. Don't keep rolling it because it's what you want it to be. So 2 natural questions are, how many rolls do you expect before you have double sixes showing? And another one is, what's the probability you win on your first turn or your second, or more generally on your end? So can we use the Darth Vader theorem here? Why or why not? So again, this is a good place to just stop and think for a moment. All right, welcome back. So it's a little bit hard to use the Darth Vader problem. We will use it later. We will find a way. But what makes this hard is that the probability of success is not constant. It depends on whether or not we rolled a 6 earlier. So we need a new method. So let's look at the second question that was asked. What is the probability we win on the first roll? I will let you pause and think for a moment. Welcome back. So the answer is just 1/36. We will consider the 2 die distinct, say left die, right die, and we need a 6 on the first, which happens 1/6 of the time. And we need a 6 on the second, which happens 1/6 of the time. And 1/6 times 1/6 is 1/36. Now, what's the probability you win on the second roll? This one is a little bit more involved. And so again, this is a good time to take your pen to paper and play with this for a little bit and see what you can get. And here's the answer. 1036 times 1/6 plus 2536 times 1/36. Why is this the case? Well, for problems like this, I find making a tree diagram is really good to enumerate the possibilities. So on our first roll, we could get 2 doubles, we could get 2 6s, and that happens 1/36 of the time, and we're done. Or maybe we get no 6s. How many ways are there to get no 6s? Well, there's 5 choices for the first die and 5 for the second. So 25 out of the 36 pairs will have no 6s. So that means since there are 36 pairs total, and we've accounted for 25 plus 1 is 26, there must be 10 pairs with exactly 1/6. So if we roll exactly 1/6 on the first turn, then we only need to roll 1 die on the second, and the probability that we get a 6 is just 1/6. So this is where the 1036 times 1/6 comes from. We are here 1036 of the time, and then from here, 1/6 of the time, we get the remaining 6. If, however, we rolled no 6s, then to win on the second turn, we would have to roll double 6s, which happens 1/36 of the time. And so we see the probability of winning on the second roll is 85 over 1296. So we can continue this analysis, but it's going to get more and more involved as there's more and more branches. And so we're going to introduce a wonderful idea in probability, the law of complementary events. So if the probability something happens is P, then the probability does not happen is what? Well, let's think about it. If something happens 80% of the time, then it doesn't happen 20% of the time. And so if the probability that something happens is P, and the probability it does not happen is just 1 minus P. And the other idea that we need for probability is the law of double counting. So imagine you have 2 events A and B, and maybe they could both happen. and you want to know the probability that A or B happens. And this is the inclusive OR. If they both happen, that's fine. So the probability that at least one or maybe both of them happen is the probability of A plus the probability of B minus the probability that they both happen. And so we can see this by drawing, this oval will represent all the times A happens. That's the pink oval. And the blue oval will be all the times B happens. And then the stuff in the intersection, the purple area, is when both A and B happen. And so here is just A, here's just B, here's A and B. So we've double counted this area because we counted it under the probability of A and under the probability of B, and that's why we have to subtract. If you wanted to know the probability that exactly one happened, we'd actually subtract off twice that. And so now we can use this to figure out what is the probability we win by the nth term. That's not saying that we won on the nth turn, it's just after we have n rolls, we know we've won. Well, by the law of complementary events, it's 1 minus the probability we have not won by the nth turn. And it turns out that that probability is easier to calculate. And this is why the law of complementary events is so useful. Sometimes when you have an event, the probability that it doesn't happen is easier to calculate than the probability it happens, or vice versa. So what is the probability we haven't won after n rolls? So I'm going to pause the video and let you think about this for a moment. Welcome back. And so what is the probability we haven't won after n tosses? It's 5/6 to the n plus 5/6 to the n minus 25/36 to the n. So where does this come from? Well, let's let A be the event that the first die is a 6, at least once in the first n rolls, and B be the event that the second die is a 6, at least once in n rows. So if in n rolls we never have a 6 in the first die, that happens 5/6 to the n times. Each roll has to be a non-6. Similarly for the second die never being a 6 in n rolls. But we've double counted the case when neither die is ever a 6. And so we've shown before that if you roll 2 die, the probability you have no 6 is 25/36. And that's where this comes from the double counting. So now we know that the probability we win by the nth turn is 1 minus 2 times 5/6 to the n plus 25/36 to the n. It was just 1 minus the probability we haven't won. So what is the probability we win on the nth term? This is the probability we win by the nth term. So if you know the probability you win by the 4th term and by the 5th term and by the 6th term, can you figure out the probability you won on the 5th term? So I'm going to pause and let you think about this for a moment. Okay, welcome back. Well, if we know the probability we win by the 4th term, and we know the probability we win by the 5th term, and if we look at the difference, that will be the probability we won on the 5th term. So for example, if you win by the 5th term 85% of the time, and you win by the 4th term 80% of the time, then the probability you won on the 5th term is just 85 minus 85%. So we have the two probabilities. We have the probability that we win on the nth term, and we subtract the probability we win by the n minus first roll, and that difference is going to be the probability we win on the nth term. So if you just do some algebra, you can see the 2 1s will cancel. The negative here, well, the negative of a negative is going to be a positive, so we'll have 2 times 5/6 to the n minus 1 minus 2 times 5/6 to the n, and we can pull out a 2 times 5/6 to the n minus 1. And when you just do all the algebra, which I urge you to do, you get 2/6 times 5/6 to the n minus 1 minus 11/36 times 25/36 to the n minus 1. Okay, so now we have a claimed probability of winning on the nth term. Is this right? Well, whenever possible, it's good to do some computer simulations to check. And so what I did is I played the game on my computer 100 times, about 10,000 times, and 100,000 times. It was taking a bit too long to do a million, so I just quit it. And if you look over here, the blue dots are the theoretical predictions. It's not bad, but it's not perfect with 100 trials. With 10,000 trials, it's pretty good. And with 100,000 trials, it's amazing how close those are. So these are histogram counts, and these are just showing how many times, or what percent of the time it took exactly 5 rolls to win the game, or 6 rolls to win the game, or 7. And we can see what is the most likely roll to win on. And that's a little bit different than the expected number of rolls we need to win. And we'll talk about that in a moment. So here was the code that I used to simulate this. I did not bother putting in comments, which is a really good thing to do, but I strongly urge you to learn how to program. If you can simulate games and results, that's incredibly valuable. So now we want to calculate the expected value, the number of rolls you need before you win. And we're going to use a stronger version of the Darth-Vader theorem. So the Darth-Vader theorem said that if the probability of success is p, then the expected number of trials until the success is 1 over p. But we got that by looking at this infinite sum, p times 1 plus 2 times 1 minus p plus 3 times 1 minus p squared plus 4 times 1 minus p cubed, and so on. And if you notice that the number here is always 1 higher than the exponent. And this is because 1 minus p to the 0 is just 1. So we have this stronger version, this infinite sum, and we're going to find a way to see that infinite sum in the problem we have now. And this is one of the greatest challenges, is noticing what you have can be rewritten in a way to equal something you've already done. That's a great skill to get. And so to compute the expected number of rolls until the double six game ends, we need to compute the sum of n times the probability takes exactly n rows. And n goes from 1 to infinity. So we know the probability takes exactly n rolls is just the following here, 2, 6, etc. And we're going to introduce some notation. This is the Greek capital S, capital sigma, and we use that because sigma and sum, they're both S. And this is read the sum n goes from 1 to infinity of a sub n. It means keep this quantity here and replace n with 1, and then with 2, then with 3, 1, 4, which is a compact way of writing it. So this is going to just be a1 plus a2 plus a3, and so on. So our sum is the following. It's the sum of n times this expression. And we can pull out some things. And so what we can do is, this accidentally superscripted, but hopefully it's understandable. We can pull out a 2, 6 from the first term. It will have, when n is 1, we'll have 1 times 5, 6 to the 0. When n is 2, we'll have 2 times 5, 6 to the 1. When n is 3, we'll have 3 times 5, 6 squared. So you can see it looks very similar to what we have up over here. And so the question is, when you pull things out, this looks a lot like the Darth-Vader theorem. We need to figure out what p should be for the first term and what p should be for the second. So we want this to be the same as this. So if you look at it over here, they both have 1s, they both have 2s. This is a 1 minus p and this is a 5, 6. Both have 3s, 1 minus p squared, 5, 6 squared. What do you think p should be? So I will pause the video and let you think about this for a moment. Welcome back. When you look at this, we want 1 minus p to be 5, 6. So p should be 5, 6 for the first term. And for the second, it should be 1 minus p is 25, 36. So p should be 11, 36. And so when we substitute in, we now have something that looks exactly like the Darth-Vader theorem. So we can use the Darth-Vader theorem to evaluate the sum. And I'm now writing it exactly in this form. P is 1, 6, and then there's the infinite sum. And the second is minus 11, 36, and there's the infinite sum with a minus 11, 36. So I will pause and let you think about what this should be. Welcome back. Well, this sum here should just be 1 over p, where p is 1/6. This should be 1 over p, where p is 11/36. So since we have a factor of 2, the first is 2 times 1/6, and the second is just 1 over 11/36. And so when we add them, or actually subtract them, we get 96 11s, or about 8.7 rolls until you get double sixes. So whenever you get an answer in math, you should always ask, is this reasonable? Are you surprised? Is there any way you could find out if this makes sense? Maybe find an upper bound or a lower bound. So an upper bound means it can't be larger than this. A lower bound means it can't be lower. So I'm going to pause and let you think about that. And so if we go back to the 6th game, this is the reason we started with it. Well, if we roll just 1 die, and we saw that that took at least 6 turns on average to get 6, we shouldn't be able to get 2 6s on 2 dice faster than that. So that should be a lower bound. So we get a lower bound of 6. And then for an upper bound, imagine we play the 6th game on the first die, and then once we get a 6 on that, we stop, and then we start playing the 6th game with the second die. And if we add those two, that should be an upper bound, because that never allows the 2 die to be rolled together. And that would give you an upper bound of 12. We can actually make it a little bit better. We can make it 11, because we know at least one of the rolls of the second die has to be one of the rolls of the first die. So just to review, what are the big takeaways from today? Well, the first was the Darth-Vader theorem, which we had before, that if you have a probability of success p, then the expected number of trials until a success is 1 over p. But even more importantly, we had an infinite sum. And then the next is the law of complementary events. If the probability something happens is p, the probability it doesn't happen is 1 minus p. We then had the law of double counting. The probability that a or b or both happens, is the probability of A plus the probability of B minus the probability that they both happen. And the last is the power of algebra. Sometimes you have to do a little bit of algebraic manipulations to take what you have and arrange it so it's something that you see, that you've seen before and understand. So for next lecture, we're going to do, I think, more calculations on bridge. So I hope you enjoyed today's talk. Be sensible, have a great day,